Assalamualaikum warahmatullahi wabarakatuh. My name is Helmarini Endang Febti with student identification 195, chemical engineering student from Universitas Pembangunan Nasional Veteran Yogyakarta. Hi everyone, thanks so much for watching this video. I'm really excited to share something that I think is both fascinating and important. So today we are diving into a study called the use of ionic liquid for solubility enhancement in eco-friendly industries. Okay, I know that title might sound a little bit technical, but don't worry. This is all about tackling a real world problem, managing waste, especially from the fisheries industry, in a way that's good for the environment and good for business. And trust me, there are some pretty cool idea in here about how we can make that happen. Okay, so green chemistry is all about making chemistry better for the planet and for us. It's like asking how can we design products and processes that are safe, clean, and efficient? How Imagine creating stuff without creating a mess. No toxic chemicals, no waste, just good vibes for the environment. Now, this idea is guided by these 12 principles of green chemistry. They are like a checklist for how to do chemistry in a way that's friendly to Earth. Things like preventing waste, using safer materials, and even making sure the products break down naturally when we are done with them. And here's the best part: green chemistry isn't just about science, it's about making differences. It's directly linked to global efforts like the United Nations Sustainable Development Goals. So, by embracing these principles, we're not just protecting the environment, we are also paving the way for a healthier, more sustainable future. So, basically, green chemistry is a branch of chemistry that focuses on designing chemical products and processes that reduce or eliminate the use and generation of hazardous substances. It emphasizes sustainability, environmental safety, and efficiency. Below are the key types or principle of green chemistry. The first one is prevention of waste. So the goal is the most effective way to reduce waste is to prevent it from being generated in the first place. This can involve designing process that minimize the production of unwanted byproducts. For example, is reaction that only produce desired products with no byproducts or waste. And the second one is atom economy, a method that maximizes the incorporation of all materials used in the process into the final product. High atom economy means fewer raw materials are wasted. For example, reaction where most of the atoms in the reactants end up in the final products, reducing the need for waste management. And the third one, there is less hazardous chemical synthesis, designing synthetic method that use and produce substances that are less harmful to human health and the environment. For example, using water or safer solvents in place of toxic chemicals like benzene or chlorophyll. And the next one is designing safer chemicals. So developing chemical products that are less toxic, biodegradable, and safer for humans and the environment throughout their life cycle. For example, is when formulating chemicals that are biodegradable, reducing their environmental persistence. The fifth is safer solvents and reaction condition. Choosing safer solvents, avoiding toxic solvents like chloroform, and designing reaction to take place under milder condition, like lower temperatures, ambient pressure. And the example of this key is substituting traditional organic solvents with water or ionic liquids. And the next one is energy efficiency, of course, reducing energy consumption in chemical processes by designing a reaction that occur under mild condition. room temperature as atmospheric pressure. For example, is optimizing reaction conditions to require less energy, such as using catalyst and work at lower temperature. And the seventh one is renewable feedstock, using renewable non-toxic raw material instead of fossil resources to produce chemicals. And for example, using a plant-based feedstock. And next one is use of catalysis. Catalysis, so utilizing catalysis to increase the of chemical reaction, often reducing the need of harsh chemicals or high temperatures. And for example, is enzyme catalyzed reaction or metal catalyzed inorganic synthesis, reducing the need for additional reagents. And the next one is real-time analysis for pollution prevention. The goal is implementing real-time monitoring to identify and minimize pollution during chemical processes, preventing the need for end-of-pipe treatment. And for example, is using sensors to detect byproducts or pollutants in industrial processes and adjusting them in real time. And the last one is designing chemicals and product for degradation. The goal is creating chemicals that can be easily broken down in the environment, thus avoiding long-term pollution. For example, designing biodegradable plastics that degrade into non-toxic substances after use. So, green chemistry has made significant strides in various industries, driving sustainability, improving resource efficiency, and reducing environmental impact. Here are some examples of how green chemistry is applied in industry. So the first one is biodegradable plastic. Companies like Nature Works use renewable resources like corn to produce polylactic acid, a, biode- a biodegradable plastic. This plastic is used in food containers and bottles, reducing reliance on petroleum-based plastic and mitigating environmental pollution. The second is pharmaceuticals. The pharmaceuticals industry companies uh, like Pfizer have green embraced embraced green chemistry to reduce the environmental impact or drug manufacturing. For example, replace previous metals like palladium with cheaper and more abundant uh, abundant alternatives like nickel in drug synthesis. This substitution reduces waste and lower cost. Additionally, the company adopted continuous manufacturing processes, cutting waste and improving productivity by 56%. And the third one is green paints. So the paint industry has adopted green chemistry principle to create safer, uh, eco-friendly products. For example, Sherwin-Williams developed water-based uh, acrylic paints that contain fewer volatile organic compounds. These are these paints are made using ingredients like soybean oil and recycled PET bottles, reducing the environmental footprint. And next, sustainable manufacturing. In manufacturing, companies are moving towards less toxic and more efficient processes. For example, Dow Chemical and Koehler developed a new method for producing thermal paper without the use of bisphenol A, replacing it with a safer polymer coating. And the last one is energy efficient chemical processes. Green chemistry has also made an impact on energy efficiency. Processes have been developed that require less energy, such as the creation of high performance coatings, use environmentally friendly processes that consume less power compared to traditional methods. These examples show how green chemistry is transforming industry by not only reducing environmental harm but also enhancing products' performance and effectiveness. Uh, it's a win-win for both business and the planet. First, we will talk about the global problem of bio-waste. what is it and why is it such a challenge. Then I'll introduce you to ionic liquids and explain why scientists are so excited about them. After that, we will look at the experiments and results from the study to see what worked and why. And finally, we will wrap up with some ideas about how this research could be applied in the real world. Okay, so I think that sounds good. So, great. Let's start by talking about the problem we are trying to solve. So the first one is biowaste. So biowaste have a large volume of waste, environmental impact, and the biowaste potential. So global fisheries production is at a record high and is expected to continue increasing to meet future food and nutrient needs. However, fish processing generates huge waste, including scales, skin, heads, bone, and fins. This waste is often simply thrown away, creating environmental problems. And what are the impacts? So, organic waste from poorly managed fisheries can cause water and soil pollutions, greenhouse gas emissions from decaying organic matter. Pollution from this sector is great concern for sustainable resource management. And what are the potential? Fish waste is actually rich in high value compounds such as collagen, amino acids, uh, that essential components that can be extracted from protein residues. And with the right technology, this waste can be utilized with as a resource instead of just waste. So here we see a massive challenges, but also a tremendous opportunity to manage bio-waste sustainability. And how do we address this issue? One promising approach is the circular economy. What is circular economy? So, circular economy is a concept to maximize resource use, minimize waste, and promote sustainable production and consumption patterns. This approach supports global efforts to reduce the exploitation of natural resources. And what are the real events in the fishing industry? So, biowaste from fisheries offers great opportunities for application in the circular economy, like extraction of high value materials, turning waste into value added products such as collagen and gelatin. So, collagen is a protein that can be used in food cosmetics and pharmaceuticals. And then waste reduction, reducing waste discharge into the environment, and resource efficiency, using advanced technology to improve efficiency in processing raw materials. So, to achieve sustainable waste management, innovation is required in extraction technology of high value compounds and the use of uh, environmental friendly alternative solvents. However, traditional solvents currently used in these processes pose significant limitation. What are the problems with traditional solvents used for waste management? So the first problems is with organic solvents. So conventional organic solvents are often used to extract proteins or amino acids from waste, but have limitation such as toxicity. Many organic solvents are toxic and pollute the environment, and low efficiency. Traditional solvents are not always able to dissolve biomolecular compounds well. And the last one is unsustainable. The production of use of organic solvent is not in line with circular economy principles. And uh, this is need a n- need a new solution. Importance of new solution such as efficient, safe, and environmental friendly alternative solvents are needed to replace traditional solvents. And this ionic liquids is a new generation of solvents with a high flexibility overs and a offers a potential solution. This underscores the need for safer, more efficient, and sustainability alternatives. So this is where ionic liquids or ILS emerge as a promising solutions. So ionic liquids offer numerous opportunities across various industries due to their unique properties such as low volatility, high thermal stability, and tunability. And below are some significant opportunities. The first one is advanced energy storage. For example, like electrolytes for batteries. Ionic liquids are being explored as safe as efficient electrolytes in lithium ion and sodium ion batteries, offering improved stability and capacity. And then there's supercapacitors. So ionic liquids enhance energy density and performance in energy storage system. The second one is green chemistry and sustainable processes. So, ionic liquids as alternative solvents, they replace toxic organic solvents in chemical reactions, aligning aligning with green chemistry principles by reducing water and hazardous emissions. And there's catalyze. So ionic liquids are used in homogeneous and heterogeneous catalysts, enabling high selectivity and efficiency in chemical transformations. And the third one, there's environmental application. So ILs can have been developed for efficient absorption and capture of carbon dioxide, help mitigate climate change impact, and they can also enable the selective extraction of heavy metals and organic pollutants from water, promoting cleaner water system. The fourth one is pharmaceuticals and biotechnology. So, ionic liquids are used as solvents or stabilizers for poorly soluble drugs to improving bioavailability, and they create optimal environments for enzyme catalyzed reactions, boosting efficiency in drug synthesis. And for the last one is renewable energy. Ionic liquids serve as media in processes like electrolysis for hydrogen generation, and they facilitate the breakdown of lignocellulosic biomass into biofuels. So, what is ionic liquid? Based on the book Ionic Liquids and Their Application that was published in 2023, ionic liquids are normally defined as compounds completely composed with ions with melting points below 100 degrees Celsius. The first ionic liquids, ethylammonium nitrate, was reported by Paul Weldon in 1914, who at the time never realized that ionic liquids would become a major scientific area after most one century. Actually, ionic liquids as innovative fluids have received wide attention only during the past 2 decades. The number of papers published about ILS has exponentially increased from a few in 1996 to more than 5,000 in 2016, exceeding, exceeding the annual growth rates of other popular scientific areas. This indicates that more and more researchers are engaged in studying this exciting area, with the outcomes being plentiful. A multidisciplinary study on ILS or ionic liquids is emerging, including chemistry, material science, chemical engineering, and environmental science. More specifically, some important fundamental viewpoints are now different from the original concepts, as insights into the nature of ILS or ionic liquids become deeper. For example, the physicochemical properties of ILS are now recognized as ranging broadly from the quoted non-volatile, non-flammable, and air and water table to those are distinctly volatile, flammable, and unstable. This is attributed to numerous combination of cations and anions that meet the definition of ionic liquids, leading to the first suite of behaviors. Regardless, ionic liquids remain more desirable than conventional volatile solvents or or catalyzed in many physical and chemical processes, often exhibiting green and designer properties to a useful degree. Next, I'm going to talk about the solutions of our problems in biowaste and fishery industries, like I've said before in the previous slide. So this is one of the research about the solubility of seven amino acids in two acetate ionic liquids from 298.15 Kelvin to 328.15 Kelvin. And the authors are Paula Soto Montero, Eva Rodil, and Ana Soto. The journal is from Fluid Phase Equilibria, and it was published on 2024. So what is the basic idea behind this journal? So this research is all about two things that seem pretty unrelated at first: amino acids and ionic liquids. But trust me, they come together in a really interesting way here. So let's talk about amino acids. You've probably heard about amino acid before. They are like the building blocks of life, essential for proteins and super important in biology. Now, in this study, the researchers look at seven different amino acids, including familiar ones uh, like glycine and valine. These little molecules are not just useful for biology, but also have a huge potential in industrial applications. Now, here's where it gets even cooler. To work with amino acids, you need a way to dissolve and separate them efficiently. That's where ionic liquids come in. They are these amazing customizable solvents that are a lot of more eco-friendly compared to traditional ones. So, what's the goal here? The researchers wanted to figure out how well these amino acids dissolve into specific ionic liquids, such as C2-MIM-OAC and C6-MIM-OAC. So those are types of ionic liquids, which are salts that are liquid at or near room temperature. So what do they stand for? So the C2-MIM, this refers to the cation positively charged part of the ionic liquid. C2 means it has two carbon chain, and MIM stands for 1-ethyl trimethyl trimethylimidazolium, which is a type of imidazolium-based structure commonly used in ionic liquids. OAC stands for acetate, which is the anion negatively charged part of the ionic liquid, and C6-MIM-OAC. So the C6-MIM is um, similar to the C2-MIM, but it has six carbon chains instead of two. And the OAC also stands for acetate. And they tested this across a temperature range from to 298.15 Kelvin to 328.15 K. They are trying to understand not just how soluble these amino acids are, but also how temperature affects their behavior. And why this matter? Well, this kind of data is super useful if you are designing greener and more efficient processes, especially for industries dealing with biowaste or biomolecules. It's like solving two problems at once, making chemistry more sustainable and getting valuable resource for waste. Okay, that's the basic setup of this journal. Let's dive deeper into this why matters and how they actually did it. So next I'm going to explain the experimental design. So some amino acids that can be found in fish residues, such as skin, fins, or scales, were selected as target biomolecules for solubility studies. So sources are and purities are shown in the the information in table 1 on the journal. I'm going to show it in the next slide. So the acetate ILS or ionic liquids were purchased from Lolitech prior to use. Prior to their use, they were dried under vacuum at moderate temperature for 48 hours to confirm chemical structures and the absence of significant impurities to 1H and uh, 13C NMR spectra were carried out. Water content was also measured by the Carl-Fisher titration method in a Metrum 899 colorimeter. Water content was less than uh, 1000 ppm for all the batches used of both ionic liquids. Density of pure ionic liquids is presented in the table with literature values. To prepare aqueous mixtures of the ILS, distillized water was used. So first, let's take a look at the materials used in the study. The experiment involved seven amino acids. There are glycine, L-alanine, L-valine, L-serine, L-threonine, L-leucine, and L-isoleucine. These amino acids were selected because they have different properties such as molecular size and polarity, which could influence their solubility. Then there's two ionic liquids, like I mentioned before, C2MIMOAC and C6, which has with the C2 has a short carbon chain and the C6 has a longer carbon chain. The difference in structure was important to explore how the length of the carbon chain affects amino acid solubility. And additionally, the study used water thermostats to maintain the temperature of the solution during the measurements. The temperatures tested range from 298.15 K Kelvin to 328.15 Kelvin in increments of 10 Kelvin. This was done to understand how temperature affects solubility. Now let's move on to the experimental procedures. So the authors prepared a small amount of amino acids that was accurately weighed using an analytical balance. Then the amino acid was added to a measured amount of ionic liquids. The mixture was stirred until it reached equilibrium, which usually took a few hours. And then the second one, to ensure consistent results, the solution were placed in a thermostat control system starting from 298.15 Kelvin and increasing up to 328.15 Kelvin. And the third one is solubility measurement. Once equilibrium was achieved, the solution was centrifuged to separate any undissolved amino acid. The concentration of the dissolved amino acids in the ionic liquid was then measured using spectrophotometry. a method that is very sensitive to small molecule concentrations like amino acids. And the controlling variables, it's important to note that the authors controlled several variables to ensure the reliability of the results. So the first one is temperature. It was maintained at a constant value for each test point using the thermostat. And the second one is sample amounts. The concentration of amino acids and the volume of ionic liquid were standardized to avoid unwanted variation. And the steering time, all samples were steered for the same amount of time to ensure equilibrium was reached. So, once the solubility data was collected, the author used mathematical models to analyze the relationship between temperature and solubility. And one of the approaches used was determining the enthalpy and entropy of the solubility process, which helps explain how energy and system order change during the dissolution. And this analysis also allowed for a comparison between the two ionic liquids to determine which one was more effective in dissolving each amino acid. So overall, the experimental design is very systematic to thorough by using different amino acids, varying ionic liquid acids, and an in-depth temperature analysis. This study or this research provides a complete picture of how the solubility of amino acids can be influenced by these factors. Now, let's take a look at the results from these experiments and what we can learn from the data they have collected. So, before going to the results and the discussion, I'm going to explain the source and purities of the compounds the author used in their work. The first compound included glycine, alanine, proline, trans 4 hydroxyproline, lysine monochloride, arginine, and cysteine. So each amino acid is identified with its specific CAS chemical abstracts surface registry number to ensure clarity and precision for replication purpose. And for the source, all the amino acids were sourced from Sigma Aldrich, a reputable supplier for high purity chemicals used in scientific research. And the purity, each amino acid had a mass fraction purity exceeding 99%, confirming they are of analytical grade. And this level of purity is essential for reliable, uh, re- reproducible experimental outcomes. And the second compounds includes the ionic liquids, 1-ethyl 3-methylimidazolium acetate and 1-butyl 3-methylimidazolium acetate. The specific CAS registry number are provided for both ionic liquids, ensuring precise identification. The ionic liquids were pros, pro, procured from Lolitech, a leading supplier specializing in ionic liquid materials. And the ionic liquids were vacuum dried and heated to remove moisture, and their purity was analyzed and confirmed using NMR, nuclear magnetic resonance, and GC, gas chromatography, with a purity level of 99%. So the purpose of this table is the first one is reliability by detailing the sources, CAS numbers, and purification methods. The table ensures the material used in the study are traceable and reliable. And the second one is replicability. Other researchers can replicate the experiments using the same high purity materials. And the last one is scientific rigor. The stringent quality checks uh, and NMR and GC analysis demonstrate the robustness of the methodology. This table established the foundational quality of the experimental materials, which is critical for studying the solubility of amino acids in ionic liquids. So, in this study, the solubility of various amino acids into acetate ionic liquid C2 and C6 and their mixtures with water was evaluated over a temperature range from 298.15 Kelvin to 328 Kelvin. The goal was to explore their potential for biomolecule extraction from fish waste, particularly collagen, which contains high concentration of proline and hydroxyproline. So, based on the table two, we can get conclusion for the solubility trends in and ranking. So, proline and proline were found to have the highest solubility, making them the most promising candidates for extraction processes. However, glycine, despite being the most abundant amino acids and collagen, showed relatively low solubility in C2. Okay, so I'm going to explain the table 2, the solubilities of amino acids in C2 and its mixtures with water. So, like I said before, the table 2 presents the solubility data in mass fraction for various amino acids in the ionic liquid C2 that have uh, that have two carbon chain, and in its 50-50 ratio mixture with water measured at temperatures from 298.15 to 328.15 Kelvin. So this data is critical in understanding the solubility behavior of amino acids in ionic liquids, which is relevant for application like bioextraction from fish waste. So the amino acids included the seven amino acids that I've mentioned in the materials before. And for the observation, the solubility of all amino acids increased with temperature in both C2 and its water mixture. And and I've already said before that the proline is consistently had the highest solubility, and followed by the hydroxyl proline and arginine. The C2 system showed better solubility for most amino acids than the water mixture, especially for hydroxyl pro and lysine chloride. In contrast, glycine and cysteine showed lower solubility. The solubility of cysteine in both systems was very low, indicating a challenge in extracting cysteine with these solvents. In the mixture of ionic liquids and water, the solubility of proline increased significantly compared to pure C2, suggesting that water can enhance the solubility of certain amino acids, potentially aiding the extraction process by reducing solvent viscosity. And right down below the table 2 is there is the solubilities of amino acids in C2 and C2 water, which is like the ratio of 50-50 mixture. So 50 is C2 and the 51 and the 50 other is water. So or the figure 1 is visualize the solubility trends of the amino acids in two different solvent systems. In the panel A, the left side, the graph shows the solubility of amino acids in pure ionic liquid. Proline, hydroxyproline, and arginine show the highest solubility, confirming the prevalence for more hydrophobic amino acids in the C2. Cysteine and glycine have the lowest solubility in pure C2, indicating limited solvation for amino acids with higher polarity or smaller side chains. And the C2 plus water 50-50 or in panel B, right side, the presence of water leads to proline and hydroxyproline, showing even higher solubility, with proline becoming the most soluble amino acid. The solubility of glycine improves compared to the pure ionic liquid, but still remains relatively low compared to other amino acids. Cysteine solubility remain negligible in both systems, which could be a limitation for applications where cysteine extraction is necessary. So, the solubility of amino acids generally increases with temperature, with notable increase for arginine and proline, making temperature a crucial factor in optimizing extraction processes. The water in the solvent mixture helps enhance the solubility of certain amino acids like proline, but reduces the solubility of others like glycine and hydroproline. The presence of water also decreases the viscosity, which could be beneficial to large-scale bioextraction process. And these observations are crucial for designing efficient extraction process, especially in applications such as collagen extraction from fish waste. The authors use the Van Hoff equation to analyze the solubility data of amino acids in ionic liquids and their mixtures with water. The Van Hoff equation is a simple and useful model to correlate solubility data, and it is applied here to describe how solubility changes with temperature. The equation used is the natural log of x um, equals to A plus B per T in Kelvin, where X is the solubility of the amino acid in mole fraction. A and B are regression parameters, and T is the temperature in Kelvin. This equation helps to establish a linear relationship between the natural logarithm of solubility and the reciprocal of temperature. The results show that the equation effectively correlates solubility data across the temperature range 288.15 Kelvin to 328.15 Kelvin. So, the solubility of amino acids in both pure ionic liquids and their water mixtures follows a predictable pattern when fitted with the Van Hoff equation. Proline Pro and hydroxyproline or OH Pro exhibited the highest solubilities in both ionic liquids and their mixtures with water, aligning with the observed behavior that solubility increases with temperature. The Van der Hoef model works well to describe the solubility of amino acids in this study, providing insights into the dissolution process, including how enthalpy and entropy contribute to solubility change. This correlation allows the researchers to determine the apparent standard thermodynamic properties of dissolution, such as enthalpy, keeps free energy and entropy without needing colorimetric experiments. These thermodynamic properties indicate that the dissolution process is endothermic, requiring heat and entropy driven, which suggests that the process favors increased disorders at high temperatures. In a to sum up, the Van Hoff equation provided a simple yet effective method for analyzing the solubility of amino acids in ionic liquids, which is crucial for applications like biomolecular extraction from fish waste. Figure 3, Van Hoff correlation in C2 and its mixture with water. The panel A shows the Van Hoff correlation of solubility data for amino acids in situ across the temperature range of 298.15 Kelvin to 328.15 Kelvin. The graph uses the natural log of solubility versus the reciprocal temperature 1 per T. This linear relationship helps correlate solubility data with temperature, confirming that the dissolution of amino acids in this ionic liquid is endothermic and entropy driven. It also implies that enthalpy and entropy contribute to the solubility changes as temperature increases. And the panel B shows the same correlation for C2 mixed with water. The presence of water modifies the solubility trends, as the solubility of proline and hydroxyproline significantly increases in the mixture compared to the pure ionic liquid, while the solubility of glycine and cysteine decreases. The graph follows a similar pattern, indicating that the solubility behavior of amino acids in the binary system is influenced by the hydrogen bonding between the ionic liquid and water. And the next one is figure 4, the Van Hoff correlation in C6 and its mixture with water. The panel A shows the Van Hoff correlation for solubility data in C6. So the solubility of amino acids in C6 is lower than in C2, particularly for glycine and cysteine, which shows minimal solubility due to the more hydrophobic nature of C6. The temperature dependence is similar, with an increase in solubility as the temperature rises, suggesting the thermodynamically favorable process. The panel B, like in figure B, the presence of water increases solubility for some amino acids, but decreases it for others. This highlights the complex interaction in mixed solvents where water influences solubility through hydrogen bonding and the changes in solubilization environment. So figure 3 and 4 illustrate how solubility data of amino acids in two different ionic liquids and their mixtures with water can be well correlated using the Van Hoff equation. These figures provide insights into the thermodynamic behavior of dissolution, indicating that both enthalpy and entropy can play crucial roles in the solubility processes. The effect of water content on the solubility of amino acids is also clear, with some amino acids showing enhanced solubility in mixtures, while others shows reduced solubility. So we can get the conclusion from the research that focus on studying the solubility of various amino acids into acetate ionic liquids and their mixtures with water. The first one is their solubility trends and behavior, which includes temperature effects. The solubility of all amino acids increase as the temperature increase, indicating that the dissolution process is endothermic or requires heat. This is a typical behavior from the dissolution of many solids in solvents. The solubility of proline and hydroxyproline was notably higher than the other of amino acids, making them the most soluble compounds in both ionic liquids. And then there's ionic liquid versus ionic liquid plus water mixtures. So C2 or C2MIMOAC demonstrate higher amino acids and solubility than the C6 across all amino acids tested. The longer alkyl chain in C6 made it more hydrophobic, thereby decreasing solubility. The mixture of ionic liquid and water significantly affected solubility. Proline and hydroxyproline exhibited much higher solubility in the ionic liquid water mixtures compared to pure ionic liquids. However, glycine and cysteine showed reduced solubility when water was added, highlighting the complex solvation effect water in the mixture. And the second is importance of water in the mixtures. So the effect of water is help reduce the viscosity of the ionic liquid, facilitating better mass transfer and making the solvent more suitable for extraction process. And the hydrogen bonding between the ionic liquid and water likely played a role in altering the solubility of various amino acids. Water's polar nature helps solvate polar amino acids, especially uh, proline and hydroxyproline, but reduces solubility for less polar amino acids like glycine and cysteine. The third one is thermodynamic insight. So the thermodynamic analysis of the Van Hoff equation was used to correlate solubility data, which revealed that the dissolution of amino acids in both ionic liquids are and their mixtures is endothermic and entropy driven. The enthalpy is the enthalpy of dissolution is positive, indicating that heat is absorbed during the process. The entropy is also positive, suggesting that the dissolution increases the disorder in the system, which is typical for solutes dissolving in solvents. And the fourth is solubility ranking and practical implication. So the best candidates for extraction is proline and hydroxyproline. Uh, they emerge the most soluble amino acids on both ionic liquids and their mixtures, making them the best candidates for extraction from sources like collagen, present in fish waste. And glycine and cysteine had significantly lower solubility, which might make their extraction less efficient compared to proline and hydroxyproline. This data can be highly relevant for industry involved in biomolecular extraction, for collagen production, or pharmaceutical application. And the last one is role of ionic liquids in biomolecular extraction. So, ionic liquid as solvents uh, is potential of liquid of pot is the potential of like ionic liquids, particularly C2, as effective solvents for extracting valuable biomolecules, especially those with hydrophobic properties like proline and hydroxyproline. Ionic liquids offer advantages such as low toxicity, thermostability, and ability to dissolve a wide range of compounds, making them ideal to sustainable and efficient extraction process. And this study provides insight into how the results of the solubility study can be extended and applied to various fields, focusing on the potential impact of ionic liquids in industrial processes and future innovation. So the first one we have optimization of water content in ionic liquid mixtures. The study demonstrated that adding water to the ionic liquid mixture had a significant effect on solubility. For example, proline and hydroxyproline showed increased solubility when mixed with water. And future research could explore optimizing water content in ionic liquid mixtures to balance the benefit of reduced viscosity and improved solubility for some amino acids while maintaining the solubility of other amino acids that may be less soluble in water-rich system. Finding the ideal ratio of ionic liquid to water could enhance extraction efficiency and make the process more cost effective and sustainable, especially for large scale applications like collagen extraction. And the second one, we have exploring other amino acids. So while the study focused on seven amino acids, future work could involve testing other amino acids, particularly those with different side chains and polarities. By expanding the range of amino acids studied, the research could uncover which amino acids beside proline and hydroxyproline are most compatible with ionic liquid solvents for biomolecule extraction. Additionally, specific amino acids are critical in pharmaceuticals and cosmetics and the food industries. This research, this research could be extended to optimize the extraction of amino acids used in functional foods, drug synthesis, and bioactive compound production. The third one is improving collagen extraction. The studies showed that proline and hydroxyproline had the highest solubility in C2 and its mixtures with water. These amino acids are key components of collagen, which is a major protein found in animal connective tissues such as skin, bones, and tendons. And collagen extraction from fish waste is a growing area of interest. Future research could focus on improving the efficiency of collagen extraction using ionic liquids, as this would contribute to waste valorization and the circular economy by utilizing fish waste for high value products. The study suggests that ionic liquids, specifically C2, could provide a greener, more efficient alternative to traditional collagen extraction methods, which often use harsh solvents and are energy intensive. The next one, expanding ionic liquids for industrial application. Ionic liquids have a wide range of potential application beyond amino acid and extraction. Their low toxicity, thermostability, and ability to dissolve both organic and inorganic compounds make them ideal candidates for numerous industrial processes, including green solvents in chemical synthesis, catalysis, battery, and supercapacitor technologies. Ionic liquids can replace volatile organic solvents, and they can be used as reaction solvents or catalysts in various chemical reaction, and they can be used for research as electrolytes for improving energy storage and performance. The fifth one is sustainable and scalable process. The sustainability and scalability are crucial factors for industrial adoption. The low viscosity and recyclability of ionic liquids make them attractive for scaling up extraction processes. Future research could explore how to reuse ionic liquids after each extraction cycle, reducing waste and improving the overall sustainability of the process. In addition, the biological waste extraction, such as collagen, ionic liquids can be used in biodegradable plastic production, environmental friendly pesticide production, and water purification. These processes could contribute to sustainable industrial practices and have significant environmental benefit. And the last one is contribution to the circular economy. Ionic liquids hold the potential to contribute significantly in to the circular economy, especially by transforming waste products into valuable raw materials. By improving the efficiency and scalability of such process, ionic liquids can reduce environmental pollution and help close the loop in waste management. The use of renewable feedstocks along with ionic liquids in various industrial processes will align with the goals of reducing dependency on fossil resources and promoting sustainability. And to sum up, the future research could focus on refining the ionic liquid water mixtures, for improved amino acid extraction, testing a wide range of amino acids for solubility, and exploring industrial applications that extend beyond biomolecular extraction. These efforts will enhance sustainability, efficiency, and scalability in various industries, making ionic liquids a key tool in greener industrial process. The potential for circular economic contribution through waste valorization further emphasize the importance of ionic liquids in the future of green chemistry. The strength of the journal is the study explored the use of ionic liquids for amino acids, solubility, and extraction, which is relatively new and innovative approach in bioextraction and green chemistry. The journal provides detailed solubility data for a range of amino acids in different ionic liquids and their mixtures with water across a wide temperature range. This this thorough analysis gives a solid foundation for understanding how these solvents behave under different conditions, crucial for optimizing industrial processes. And the use of thermodynamic models like the Van Hoff equation to correlate solubility data and the interpretation of enthalpy and entropy change adds depth to the understanding of the dissolution process. And as for the weakness of the journal, while the study examined seven amino acids, it could be expanded to include a wider variety of amino acids and biomolecules. This would help to assess whether the observed trend are generalized, generalized or specific to the selected amino acids. The study focused primarily on ionic liquids and their mixtures with water, but it would have been beneficial to compare these systems with more conventional solvents. This will provide a benchmark to evaluate how ionic liquids perform in comparison to widely used alternatives. And the research is primarily focused on amino acid solubility and does not explore real-world application of the extraction processes. Practical experiments on large-scale extraction could enhance the industrial applicability of the findings.